Let's talk about another type of power function, monomial functions. Monomial functions. By the way, a good way to watch this video is, you take notes and in the margins, if you've got questions, ask those or write those questions down, and you can shoot me an email or you can ask me in class tomorrow, and we can talk about it as well. Monomial function, one term. So here we go. F of x equals k, which is a constant, or f of x equals k times x to the n, where k is a constant or n is a not or. K is a constant in this one. It's also a constant in this one. N is a positive integer. Okay, so n is a positive integer. So if we look at a couple of graphs, we're going to talk about an even function versus an odd function, and I'm going to pull up a graph here. And basically what I've done here is I've taken all of these even functions, and what I did was I'm going to graph 2x squared, x to the fourth, x to the sixth. Okay, so I'm just collapsing all these. I'm going to graph them all at one time. So I've got x squared, x to the fourth, x to the sixth, all on one graph. And I also graphed negative 1, 1, and I graphed 0, 0, and I graphed 1, 1. Well, what do you notice? What do you notice about these graphs? They all look like a U, but they get progressively skinnier. So x squared is this purple one here, it's wide. X to the fourth is this green one, it's narrower. X to the sixth is even narrower than that. And so as we stack these even functions on one another, let's draw ourselves a little picture here. So let's draw some graphs. I'm going to start out with green here. And this is going to be f of x is equal to x squared. So this is my even function here of x squared. Well, what I've got here is a parabola that looks something like this, symmetric with respect to the x-axis, and it goes up. So that's my purple one here. Should have coordinated these colors. My next one that I'm going to draw is this green one. So it goes below my x squared, but through that point. So I'm going to try to recreate this one. F of x is x to the fourth. And so if I draw in these points that I had on my other graph, this one's going to come up and like this. So kind of like that. I'm going to grab a different color here, a red. F of x is x to the sixth. My x to the sixth graph goes even below all of them, but then goes through that point and it's narrow. So it goes below the other graphs and then it's skinnier. So it's kind of tricky to draw here, but I'm going to see if I can. Below there. And then through. So as I look at these families, look at what happens. We're symmetric with respect to the y-axis, okay? And we're kind of going in the same general direction. Let's look at a cube and a fifth and a seventh, okay? So what are we looking at when we're looking at a family of these odd functions? So I'm going to turn off all these even functions. Let's turn on all the odd functions. Check out what I'm graphing here. I've got y equals x. That's my blue line. X to the third, which is the green line here. And I've got x to the fifth, which is my purple line, and x to the seventh, which is my orange line. Look, they're all going in the same general direction. And in a cool way, they all go through this negative 1, 0, 0, and 1, 1. So let's see if I can draw this. F of x equals x. That's going to go like this. And f of x equals x to the third. If I draw these points in here, see if I can sketch this. So There we go. And how do these change? So my green one is now narrower, so that's my x cubed, narrower, and my purple one, which is my x to the fifth, comes out a little bit wider. They seem to get a little bit squarer. And so maybe I'll just even grab a purple here, f of x equals x to the fifth. So these come out and they're narrower down here, but I don't know if you heard me, I'm making the drawing noise, like a whooshing noise. Okay, f of x equals x to the seventh. So even narrower. I don't like that. So these families, they look the same, these odd functions. And what we were kind of talking about was these are symmetric to the y-axis. And these are symmetric to the origin. Because we could flip them over here and then flip them down this way. So we flip them over y and flip them over x. When it's both, that's origin symmetry. Okay, and so if we're looking to sketch a graph, now we kind of know what these families of functions look like. And so I know that because this is a cube, it's going to go through this point here. So this is -1, -1. This is 1, 1. And my graph is going to go like this for y equals x cubed. Well, what does this mean? This is a vertical stretch of 2 times. Okay, so instead of being 1, 1, this is actually going to go to 1, 2. Because a vertical stretch means my vertical, my y component, gets stretched up twice. And so if I put this here, so this is now 1, 2, this would be -1, -1, goes to 1, -2, sorry, -1, -2. So now my graph looks like this. Once again, making that drawing noise. Okay? That's what a vertical stretch means, is we're going to take it and we're going to stretch it or we're going to shrink it to fit our criteria. You can pause here and try this one. I'm going to keep rolling, so if you want to pause here and try it, you can check your answer after we get done. X to the fourth goes through 1, 1. It goes through -1, 1. Looks something like this. I made it a little bit bigger so that I could have an adjustment. Well, this means it's flipped over x. And so this one's going to go to -1, -1. This one's going to go to 1, -1. And so I already know that this is my first transformation here. So I've already taken care of the fourth. I've already taken care of the negative. Well, 2/3, that's going to be a vertical stretch by 2/3, which means that this is at -1. So 1, -1 is going to go to 1, 2/3. So I'm going to put this one in here. -1, -1, a vertical stretch of 2/3. My y part is going to be 2/3. So these are -1 and -2/3. So here and here. Kind of like that. Okay? Vertical stretch, vertical shrink. Technically not a vertical stretch. It's technically a vertical shrink, but because it's 2/3, it's less than 1, so stretch would be more than 1, shrink would be less than 1. Okay? So that's graphing. Graphing the following. This is just a family of functions all sitting on the same coordinate plane. Well, I already have a picture of this. I'm going to show you. Power functions here. So I'm graphing y equals x squared, y equals x to the 0.5, so square root of x, and y equals x to the -0.5, which is, negative square root here, or 1 over the square root of x. When I graph y to the x, here's what happens. It's going to be this blue color. This one I'm going to graph in green. y equals x squared. Well, notice what we've got here. I'm going to graph them all on 1. X squared is going to look like this. Pink, we're going to graph square root of x. So square root of x is my purple here. You're going to see something interesting happen here. Okay, that's my square root function. And let's do red for this one. And my red is going to be 1 over the square root of x. So that's going to be this orange one here that comes down this way. Looks like this. Well, what do you notice? A couple of things happen. One, 2 of the graphs don't go into any other quadrant. 2 of them go into 2 quadrants. But really, look at what happens here. I've got this point right here. Well, if I look at these graphs, what is this point here? That's 1, 1. Do you think that's a coincidence? I think not. Okay, and so let's do another little exploration with a k value of 3. So, for instance, this would be same 4 functions. So y equals 3x, y equals 3x squared, y equals 3x to the 0.5, y equals 3x to the negative 0.5. I've already got them pulled up here. So power functions for k equals 3. Notice I've got 3x, 3x squared, 3x to the 0.5, 3x to the negative 0.5. If I graph them all, look at what happened. They kind of look the same, don't they? I've got my x line here. I've got my square root here. I've got my parabola, and I've got my inverse function. Well, where do they intersect? They intersect at 1, 3. Okay, that's not a coincidence. So these are at 1, 1 with a k value of 1. These intersect at 1, 3 with a k value of 3. So what do you think is going to happen if I graph them all with a k value of negative 3? So negative 3x, negative 3x squared, negative 3x to the 0.5, negative 3x to the negative 0.5. When I graph them all, look at what happens. My k value is negative 3. This one's not 1. My k value is negative 3. These intersect at 1, negative 3. My k value tells my intersection of all of this family of functions. And so when I've got these functions here, this is what happens. I've got this one here, square root function. So f of x is equal to k times x to the a. And so a could be less than 0. So that would be my 0.5. So this one zero, less than a, less than 1. A could be greater than 1. A could be equal to 1. So let's think about this for a second. My family that I just graphed, and I probably need to rewrite this one. I'm going to pull on this up here. So we'll just do it over. I've got the y equals x line. Well, if this is y equals x, that means that a is equal to 1. So that would be k times x to the a. So that would be 3 times x. Okay? And so that's that one. Another one that we've got, I'm consulting my drawing here, so I'll make sure I get this right. Goes like this. What line was that? That went up like this. Okay, that's my parabola line. That's when a is greater than 1. Okay, so that was like my y equals x squared. The other half would go over here. It could be x to the fourth, whatever. Another one is going to be this one. And that one's going to be this line here. What was that line there? This line here was my a is less than 1. That was my 0.5. So that was my square root of x. My last one, see if they'll let me change colors here, is going to come down through that point right there. And this is when a is less than 0. That was, for example, my y equals x to the negative 0.5. And they all intersect at 1 comma k. But depending on what k is, it could either be reflected over, it could be reflected over y or over x. So x is less than 0, meaning this is in the first quadrant. This would be quadrant 4, like we saw on here. Okay, this was in quadrant 4. Or we could have it in quadrant 2 or quadrant 3, any of those things. And so what we're looking at is f of x is undefined. So if x is less than 0, f of x could be undefined. For example, f of x is equal to the square root of x. What does that function look like? It looks like this, right? For x is less than 0, it's not defined. So this power function doesn't have anything else. It's only when x is greater than 0. F of x is even. For example, x squared. What would that function look like? It's like this. Well, what would happen is it's symmetric to the y-axis. And so when x is less than 0, meaning this part over here is a reflection of x is greater than 0. Or f of x is odd. For example, f of x is equal to x cubed. So it would look like this. And therefore, it's symmetric to the origin. And that would mean that this piece here is a reflection of the original over y and then over x, or over x and then over y. Okay? And so, or over x and then over y. That's what happens when x is less than 0. This is talking about the domain. The domain of x is less than 0 for any of these functions is different. Some of them are defined for x is less than 0. For example, over here, this power function of x squared is a reflection over y. Over here, the power function when x is less than 0 is a reflection over y and then over x. For example, this power function is not defined for x is less than 0. So those are the three things that could possibly happen. So what you're going to see is everything is either non-existent or it's a reflection, which is cool for us because it helps us to know end behavior. Let's do one more example. State the value of the constants k and a. Describe the portion of the curve that lies in quadrant 1 or 4. Determine whether f is even, odd, or undefined for x is less than 0. Describe the rest of the curve, if any. Graph the curve to see whether it matches the description. So, as I write this, my k value is what? It's the constant out front, so k is 2. My a value, which is my exponent, is negative 3. Okay? And so what does this mean here? Well, we don't know yet. Let's draw a little conclusion about this. we're going to graph last. And so we want to see, describe the rest of the curve, if any. We want to see if it's even, odd, or undefined. So let's test to see even or odd. Let's test even or odd. How do we test for even or odd? We've talked about this before. We're going to do f of negative x. So 2 times negative x to the negative third. We have to do a little bit of rewriting. 2 times and what I did here was I knew that because it's a negative exponent, x to the negative third is equal to 1 over x to the third. So I put it in the bottom, and I'm going to rewrite. So I've got 2 over negative x to the negative third. When I cube a negative x, I get negative x cubed. So really what I've got is 2 over negative x cubed, which is rewritten as negative 2 over x cubed. I rewrite that like that to say that I know now that I have a negative out front, and so this is really equal to negative f of x. Because what happened up here, if I would have rewritten this one, this would be 2 over x cubed. And so when I compare this one and my new one, it's negative f of x, which means that this is odd. This is an odd function. If I graph it, so describe the portion of the curve that lies in quadrant 1 or 4, determine whether f is even, odd, or undefined, describe the rest of the curve. Let's look up here for a second. My exponent is less than 0. So that means it's going to be in quadrant 1, a is less than 0. I'm showing you these two different examples. It's going to look like this. So the quadrant 1 is going to look like this. Okay? And because it's odd, what does that mean? That means it's origin symmetry. So it's going to be reflected over x and y. So it's going to go this way. And so these are this is my curve. I didn't necessarily need to graph it because I know that it's less than 0, so it's going to come down this way. It's origin symmetry because it's odd, so it's going to be reflected into the third quadrant. Okay, so that's using the properties of power functions. Here are 2 more examples. I'd like for you to try those, and tomorrow in class, if you've got questions, we'll check answers and we'll look at them together. Okay, guys? Thanks for watching, and we'll see you next time.